Okay, ladies and gents, this is going to be a worked solution to section A of the paper that you sat for your mocks. Hopefully this will give you a chance to reflect on the way that you need to approach these questions, especially what you need to be looking for or what you need to be thinking about. You'll get the mark scheme as well as this, but hopefully this is of some use. Okay, so question 1. The angle theta lies in the first quadrant and cos theta is a third. First thing is, since angle theta lies in the first quadrant, I know that sine, cos, and tan are all positive. So later I'm going to be taking square roots, and I'm always going to be taking the positive square root. So write down the value of sine theta. So part A. To get sine theta, I'm going to use the relationship that sine theta plus cos theta is 1. Sine squared theta plus cos squared theta is 1. So cos squared theta is a ninth. Sine squared theta plus a ninth is equal to 1, which means that sine squared theta is 1 minus a ninth. So that's 8 ninths. Which means that sine theta is equal to positive root 8 over 3. Part B. Find the value of tan 2 theta. Tan 2 theta. First thing I'm going to do is look up tan 2 theta in the formula booklet. So, topic 6, calculus. Paper version is probably easier. Okay, in the trig, tan 2 theta is 2 tan theta over 1 minus tan squared theta. So 2 tan theta over 1 minus tan squared theta. So if I'm going to be able to evaluate that, I need to know what tan theta is. Well, I know that tan theta is sine over cos. So that's root 8 over 3. Sine I've already evaluated. We're told that cos is 1 over 3, so that's just root 8. Tan theta is root 8. So tan 2 theta must be equal to 2 root 8 over 1 minus root 8 squared, which is obviously just 8. So that's 2 root 8 over 1 minus 8 squared over minus 7. Or if you prefer, minus 4/7 of root 2. Rationalising that. Part C is find the value of cos theta over 2. Well, there's no formulas for cos theta over 2, but there is formulas for the double angles. So going back to here, that's handy, isn't it? There's the formula for the double angles, but actually I'm going to want to use this one that just uses the cos. So I've got cos 2 theta is equal to 2 cos squared theta minus 1. And if I'm replacing theta with theta over 2, I get cos theta is equal to 2 cos squared theta over 2 minus 1. They're the same relationship, replacing theta with theta over 2. So cos theta I know, I was told it was a third. It's 2 cos squared theta over 2 minus 1. So this is just a bit of rearranging. Add 1 to both sides, you get 4/3. 2 cos squared theta over 2, divided by 2, we get 2/3. It's cos squared theta over 2. Take square roots of both sides, you get the square roots of 2/3. And you are asked to give that in a particular form. There's root A over B, so I want you to rationalise that. As a rule, you don't have to, but this time they tell you to, so you do. So I'm going to multiply that by root 3 top and bottom, and I'll get root 6 on top and 3 on the bottom is equal to cos theta over 2. That's question 1. Question 2, all about roots. Part A is the easy part. Write down the numerical value for the sum. Well, the sum is just minus 45 over 9, which is 45 over 9, which is 5. And the product, so that was, the first one was minus b over a. So I'll write that in. And the product is minus d over a. So that's minus 40 over 9, 40 over 9. Doesn't simplify that one. Part B. It tells you the roots of this equation are 3 consecutive terms are an arithmetic sequence. So whatever the 3 roots are, they are alpha minus beta, alpha, and alpha plus beta. And I know that the sum of them is 5. So alpha minus beta plus alpha plus beta is equal to 5. Well, that just means I've got minus beta here, plus beta there. 3 alpha is 5, so therefore alpha must be 5/3. So that's how to get alpha. I still need to find beta. I haven't used the product yet. So the product we know is 40 over 9. It must be alpha minus beta times alpha plus beta is equal to 40 over 9. Now, I know alpha is 5/3. You can also spot that that's going to be the difference of 2 squares, so that will make things easier. So we get alpha times alpha squared minus beta squared is equal to 40 over 9. Substituting an alpha that we know, 5/3 times 25 over 9 minus beta squared equals 40 over 9. Divide both sides by 5/3. Get 25/9 minus beta squared is equal to 40 over 9 times 3 over 5. This is the non-calculated paper, so there is a bit of calculation here. It's 8/3. Rearrange that, we get 25 over 9 minus 8/3 is equal to beta squared. Let's get that back up. It's going to be 9/24. So that's, oh look at that, 1/9. It's beta squared, which means, strictly speaking, beta is plus or minus 1/3. But it doesn't really matter, because to get my 3 roots, I'm going to add beta and I'm going to subtract beta. So if I add 1/3 and take away 1/3 from alpha to get my 3 roots, it'll be the same as if I take away a -1/3 and add a -1/3. So I'm just going to, without loss of generalization, choose beta to be positive. And my 3 roots are Well, alpha was 5/3. Alpha minus beta would be 4/3. And alpha plus beta would be 6/3. Or 2. And there's my 3 roots. Question 3. Probability. Bag contains 3 balls numbered 1, 2 and 3. Bill selects one of these balls at random and he notes the number on the selected ball. Then tosses a number of fair coins. Tosses that number of fair coins. So he's either tossing 1, 2 or 3 fair coins. If you think about this like a tree diagram, there's 3 possibilities for the balls, all equally likely. And then for that coin there's only heads or tails. For that coin there's 2 branches, and for this coin 3 branches. 8 possible outcomes. And the question is, find the probability of no heads. Well, that's the same thing as saying what's the probability that they're all tails. So that's the probability of 1 times the probability of 1 tail. That's this first branch here. Oops, not like that. Then the next branch, add on, probability of choosing ball number 2, and then the probability of getting a tail, and the probability of getting another tail. That's this branch. And then probability of getting 3, and then tossing 3 tails. Those probabilities are easy to calculate. The first one is 1/3 times 1/2. The second one is 1/3 times 1/2 times 1/2. And the last one is 1/3 times 1/2 times 1/2 times 1/2, which is 1/6 plus 1/12 plus 1/24. And again, if I want to write this as a single fraction, it's 7/24. That's part A. Part B. The question is, given that no head is obtained, so find the probability to toss 2 coins. So the probability to toss 2 given no heads. Which is the same, and we calculate this using, again, you can find this formula in the formula booklets under probability. Where's it gone? Probability of A given B, there it is. Additional probability. Probability of A and B divided by the probability of B. So A and B is probably getting 2 and getting no heads, divided by probability of getting no heads. Now here's the thing, we've already worked out both those numbers. The probability of getting 2 and no heads was my green line in the equation above, which works out to be this fraction here. And the no heads bit, it's not very easy to read now, is it? The no heads bit is the total, it's the answer from before, that's what we worked out. So, that's 2 24s, keep everything over as 24s, over 7/24, which is just 2/7. So that's our answer to question 3. Question 4. Determine the expectation of x. Well, for continuous probability density functions, the expectation of x is equal to the integral of x times f of x with respect to x over the whole range, which in this case is 0 to 1. So we're just integrating from 0 to 1. Oops, the way there. X times 12x squared 1 minus x with respect to x. It's going to be the easiest way to do that is going to be to expand everything out. 12x cubed times 1 minus x, or 12x cubed minus 12x to the 4. And if you integrate 12x cubed, you get 12x cubed. Oh, power goes up 1 over 4 minus 12x to the 5 over 5, evaluated from 0 to 1. Obviously, you can cancel that down to be 3. Yeah, 3 times 1 to the 4 minus 12 fifths of 1 to the 5, and the 0 bits aren't going to matter anyway, are they? So 3 times 0 to the 4 minus 12 over 5, 0 to the 5, it's just going to be nothing. So that's 3 minus 12 fifths, which is 15, minus 12 over 5, which is 3 fifths. That is part A. Part B asks for the mode. The mode, as you know, for years and years and years, is the most common. What does that mean for a probability density function? It means the maximum value of f of x. How do we find the maximum? By looking for stationary points of our function f of x. So f of x was equal to, scrolled off the screen there now, and I've forgotten what it was. 12x squared brackets 1 minus x, or 12x squared minus 12x cubed. It's going to be easy to differentiate if it's written like that. So looking for stationary points, differentiating, get 24x minus 36x squared is equal to 0. Solving that equation, x, I can divide it all by 12. Let's do that first. 24x, no. Divide it all by 12, I get 2x minus 3x squared is equal to 0. X times 2 minus 3x is equal to 0, which means either x is 0 or x is 2 over 3. 2 over 3. Therefore, the mode is x is 2 over 3. The mark scheme doesn't actually require you to check that that's the maximum. But a quick substitution in, you can see that f of 0 is 0. There's actually another possibility with functions defined like this, piecewise, which is there's a possibility that you could have a local maximum here that we've just calculated, a stationary point, but an absolute maximum here that's not a stationary point. So it's probably worth just checking what's f of 1. Well, the answer is f of 1 is also 0. So the only possibility for a maximum is that x is the maximum, and therefore that's the mode. That level of rigour wasn't rewarded in the mark scheme though, just to be aware. Okay, question 5. Question is, first part is even, odd or neither? Well, to evaluate if a function is even, you look at what happens to f of minus x. If it ends up being the same, it's even. If it ends up being negative, what you started with is odd, and any other situation is neither even nor odd. So, f of minus x is equal to 2 cos of minus x plus minus x times sine of minus x. Now you should know that cos itself is even. If you think about it, symmetrical about the y-axis, like that. So it's even, which means cos of minus x is just equal to cos of x. By the same logic, sine is odd. So that's minus x times minus sine x, which is equal to 2 cos x plus x sine x, which is f of x, the thing we started with, which means that f of x is even. Part B, show that f, it's not clear there, but it show that f double dashed of 0 is 0. So this is quite a long one. For 2 marks, it's quite a lot of work, I guess. 2 cos x, because you're going to end up applying the product rule a couple of times. So we've got f dashed of x is equal to, well, this bit is just going to be minus 2 sine x, but the other bit, I'm going to have to think, well, u is x, v is sine x, u dashed is 1, v dashed is cos x, so it's u dv by dx plus v du by dx, so it's u dv by dx plus v du by dx, just 1 sine x. And obviously that's going to simplify. I've got minus 2 plus 1. It's going to simplify to x cos x minus a sine x. And then we differentiate again because the question's about the second differential. Same thing again here. U is x, v is cos x, u is 1, sorry, u dashed is 1, v dashed is minus sine x. So we get u dv by dx plus v du by dx minus, and then this bit, don't forget that bit, sine x differentiates to cos x. They're going to cancel. I'm left with f double dashed of x is equal to minus x sine x. And therefore f double dashed of 0 is equal to minus 0 sine 0, which is 0, as required. And then part C, John states that because f double dashed of 0 is 0, that the graph of f has a point of inflection at 0, 2. There's a couple of ways to debate this, but the most The one that follows from what we've done is to say, well, it's obviously not true, because since f of x is even, it can't possibly have a point of inflection. F of 0 must either be a maximum or a minimum point. It must be a stationary point. Because an even function are symmetrical about the y-axis. Whatever's going on at the y-axis, it might be a maximum, but whatever's going on here must be replicated on the other side. If it's, doesn't matter what's going on here, if it's a local minimum, it must, you get the idea. Whatever's going on here, it must be a reflection, it can't possibly be a point of inflection. Okay, I'm going to leave that there for this video. Actually, I'll pick up part question 6 next time.